Okay, we are recording now. Sorry, I had a technical glitch first time. So this is a recording of kind of a session of me discussing the concepts of large language models. Everything that's hot in AI is about large language models, ChatGPT, Claude, Gemini, all those are large language models, and understanding how they work is kind of difficult, but I want to approach it as simple as possible, not trying to dive into any of the math, and just to give a kind of a base conceptual idea of what's going on. Not an expert at all. I might be wrong on some stuff. If I'm unsure, I'll let you know. And please, do your own research, of course. But working with large language models, I'm also recording this for myself to refer to later on if I struggle with, remembering any of the concepts. Okay, we're going to start with an older machine learning concept that will kind of help understand a little bit of how machines learn, and it's the perceptron and just a neural network in general. And obviously, neural networks are emulating the human brain mathematically. I do have this whiteboard. There's a little bit of a glare. I'll move the computer around to zoom in if we need to. All right. So the idea of a perceptron is like the fundamental building block of machine learning. And then we'll talk about moving that into a feed-forward neural network. And then we'll go into the transformer, which is what it's based off, or that's what large language models are based off of. A perceptron is, I'll try to get out of the glare, but a perceptron is basically just one little, some people call it just a neuron. You could also think of it as like a single neuron, I guess. And you have like some inputs like x1, x2, x3, and all these inputs are fed into our perceptron. Um, we'll talk about what these inputs might be in a second. But they're probably just numbers at the core. And each one of these is multiplied by a weight. Um, and then there's also a bias, but basically it's just going to be some output value. We'll call it Z. And that will be X1, whatever that input number is, times W1. Okay, I know I said I wasn't going to dive into the math. So let me just jot this down, X2, W2, and however many more. At the end, we add in a bias, okay? That's it. Just trying to get the concept down of it's just numbers and it's literally just like basic linear equation, just some algebra. Um, so perceptrons, very, very simple at their core. So the kind of intuition or the innovation, I should say, comes from connecting them into neural networks. Oh, sorry. The output of the neuron, that Z value, is triggered by an activation function, and it'll just kind of spit out some value. It depends on what the activation function is, but very commonly, you're going to probably see outputs just in between 0 and 1, kind of like a percentage, right? So if it's like 0.98, that's pretty high. So this neuron is very activated based on the inputs. But if it's lower, like 0.28, then you're going to have a lot less activation on that neuron. So you can do interesting things whenever you connect them into a neural network. So I'll draw a simple one here, and then I'll just do x1, x2 for our inputs, and they'll be fed into all of these neurons. So this is our input layer. And then there's going to be, sorry, I'm writing small, so I'll zoom in if I need to. I didn't zoom in on the last one. Um, but your input layer is just that. It is however many neurons you need. Actually, sorry, I drew all these connected like that. That's not really how it would work. Your input layer is where your inputs are. We called them X1 and X2. And then they're going to go into some neurons or perceptrons, And these are going to be in your hidden layer. And they connect in like that, kind of, sort of, depends. There's a lot of variables, right? How many perceptrons do you want in your hidden layer? How many hidden layers do you need? You could take a machine learning course. They'll talk about that, of course. I'm not here to describe the architecture of neural networks, although it's very interesting and I think it's fun. Let me double check we're still recording, by the way. Yeah, we're good. Okay. So the hidden layer will then be some number, right? There might be more, but in the context of transformers for large language models, there's only one hidden layer. And then these will all go into an output layer of some number of neurons. Um, and usually we just draw X to represent that because it's too many of those. But output layer, right? And so then these are going to give you just however many numbers there are on the output. I would zoom in, but really it's not super important. What is important is what kind of data and how these things can learn. So I'm going to give an example that's very, very common. And I actually have a document called Basic ML Guide that does go into all of this pretty not super detailed, but enough, you're looking at graphs, you're looking at math. But the example that's very commonly given, sorry, let me make sure I'm not in the glare. It's called the MNIST data set. And what they do is, or what they did way back, I think in the 60s, or maybe, I forgot exactly when. Um, no, 90s. Don't quote me on any of this. I'm not an expert. But this square represents an image. And they had people just write down numbers by hand, and it converted it into just a simple black and white image. So I drew a 3, right? Somebody else might come in and do a 2. That's our other image. And they wrote like thousands of just 0 through 9, right? And they just wrote all of these, and we had a big set of data, and we wanted to train a computer to recognize what an image of a 3 looks like. Now, you might know images are really just pixels, right? Just like a grid of pixels. And so the data is really seen to the computer as just a list of pixels and their values, right? However, the resolution of the image is, that's how many pixels you have. And if it's like black and white, the pixel's either on or off, right? And so, for this, it's a whiteboard. So really it's white and black, I guess. But the black pixels would be 0, quote unquote. So you have maybe a bunch of zeros, and then wherever the 3 pixels are, you get some ones. So we have this many pixels. That is our input into the neural network. So what we'll do is the input layer needs as many neurons slash inputs as there are pixels, right? So all of our pixels go into these, or yeah, sorry, input layer would be here. And then here's our hidden. And then the output layer, right? So let me draw my X's just to show they're all connected. Okay, sweet, we're not in the glare still. The output layer is going to be 10 neurons. For 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this equals 0, this equals 1, this equals 2, this equals 3, and so on. So at the end of our neural network, we literally have neurons that are lighting up, right, from values 0 to 1. And that is kind of the prediction or the guess of what number this might be. So if we input a 3, we're going to hope that the 3 neuron has a value pretty close to 1. It probably won't, especially when we don't train it. Usually, all the parameters, all the weights and the biases, and the activation functions, everything will start randomized. You just put random numbers, and then you're like, okay, this pixel times some random number plus another random number gives the value of this neuron, and then so on and so forth. Sorry, I forgot to draw my connections. It's kind of fun to draw them sometimes, but it gets old, so you just do X's. Um, anyways, so we'll try to zoom in a little bit here. But yes, the values will go from 0 to 1. Um, and that's kind of our confidence percent of how confident we are that this is a 3. We would want this to be like 90% confident it's a 3, and all the others should be really low. So we have this idea of, well, I know we gave it an input. I'm a human. I know this is a 3, but the machine doesn't at first. It's all random. It's going to give you garbage outputs. It might say that 0 is at 0.7 and 1 is at 0.8 and then 2 is at 0 and 3 is at 0.1. And, that's obviously awful. Like, how is it really confident about a 0 and a 1? That wouldn't make sense, but that could be how it starts. So to train the neural network, it's a very, very ingenious algorithm, or I guess, I don't know if you'd call it an algorithm, a process. It's called backpropagation. It uses calculus to ultimately take the actual output that we get with the random numbers, and we know what the output should be, right? It should be 0, 0, 0, 1, 0, 0, 0, 0, right? Telling us that that is a 3. Once we have this actual versus our desired, there's error between the two, and the backpropagation will then tell us how much we need to nudge these parameters to get that gap closer and closer. And as you train more and more, your actual output will get closer to your desired output. There might still be a little bit of error at the end of it, but that's fine. Once you're getting the output that you desire, that is the idea of a feed-forward neural network. It's called feed-forward because you go forward. Now, after this, there were convolutional neural networks, also very cool. Not talking about that here. And there's recurrent neural networks, kind of cool. But large language models use a transformer, which is a big, complicated thing. So let's break it down into some pieces. Um, Okay, so it will help to know a little bit of linear algebra, but again, just conceptually. I'm not like understanding what a vector is and coordinates. I will try to draw some good pictures. Okay, so now moving into the transformer, the large language model. Right. Okay, let's start with our input. This input example was pixels, just numbers for a value of a pixel, right? The brightness, the color, whatever that may be, you can assign numbers. And so it's really just learning combinations of pixel colors and outputting a digit, right? That's at its core. It's not smart, it's just doing a lot of the same stuff over and over. So with large language models, our input is words. Well, instead of just a range of values for pixels, we have like thousands and thousands of words. I forgot how many words are in the English language, hundreds of thousands at least. A lot of words are input into a large language model. So the idea is, how do we kind of numerically associate these words? And they're very, very clever with how they did it. Obviously, you could just give every word a number, go through the dictionary, A, that's number 1, and then AB or whatever, that's number 2. But they do it slightly different to try to preserve meaning in words. Um, so a very common analogy is, I'm going to draw a plot, right? So here's our Y, here's our X. And so, I can put coordinates and I can assign these to be words. So let's make this one man, and this one will be, I guess, woman, right? This is a very common example. Can we see that? Zoom in, just bringing the laptop up. Right, okay. So we've assigned these specific words, these values, and we can write them as vectors. This is just an X coordinate and a Y coordinate, and then this one is an X coordinate and a Y coordinate, which you might have seen like X comma Y, same kind of deal. But with matrices, right? you can follow the linear algebra rules and do a bunch of cool stuff. Now, the idea of the way they embedded the words in space is that if we then kind of look at two other words like king and queen, okay, if we look at these two other words, their relation should be similar. If we draw a line between man and women, right, we have a vector. And if we draw a line between king and queen, we have a similar vector. It's going in a similar direction and it's a similar length. That is what they're aiming to do. Now, obviously, there are so many words in the English language, it's not funny. It would not be practical to do this by yourself, and nobody did. They actually just let the machine learn how these relate. And we'll get more into that later on. Oh man, it's tough because also think about it. Queen could be like a female ruler, or it could be the band. So this is a very important thing. Um, that brings me into, well, we'll get to that later. But that's the idea, putting input words into a big thing. So let's go ahead and walk through a very common example. Let's make sure. Mind the glare? No. Okay. The sentence is, the cat sat on the mat. Um, You could throw this into ChatGPT, see what it says. Probably wouldn't say anything useful. Um, so sorry, let me check my notes really quickly. Yeah. Okay. So obviously, my example, I can only draw 2 dimensions on the board. We can think of 3 dimensions in space, so you can put points in space. But the way that they chose to, it's called the embedding dimension, for our words to represent them, is they chose the embedding dimension to be 4096 for ChatGPT or maybe DeepSeek. I recently skimmed through the DeepSeek paper, um, but again, I'm not an expert on this. But this is just like your decision, right? This is just uh, a big trade-off in anything computer related, but especially large language models, is efficiency versus accuracy. And so this was probably chosen to balance those two, right? You could make it bigger, but then it's not efficient. You can make it smaller, it's not accurate, something like that. So there are literally just 4096 numbers representing the coordinate of each word. Let me actually phrase this a little different because large language models use tokens, and we, for this example, we are going to break up our tokens word by word. In real life, sometimes it's parts of words that count as a token. Um, but the input are your tokens. So we're going to say the is one, cat is another, sat on the mat, period. We have 7 tokens. However, whenever you input something into like ChatGPT, there's extra stuff as well. It's got system tokens that are like, you are a helpful AI assistant. Your job is to blah, blah, blah. That's a whole paragraph, or whatever. There's like guardrail tokens that help keep it, corporate, I guess. ChatGPT will like not, it's not going to try, it tries not to give you bad advice. It totally can. But regardless, there's a lot of extra tokens. Your prompt is kind of at the bottom. So something as simple as the cat sat on the mat being 7, it's probably going to get chunked in like a couple hundred tokens just for that one prompt. But for this example, this is all we're going to look at for our input, the cat sat on the mat. And so we've got like a bunch of numbers, right? X1, X2, X dot, 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 dot. And then the cat has its own embedding. And these are kind of learned, right? Dot, 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 dot. Sat, da, 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 and so on. And this is where a little linear algebra can be helpful if you're like, I know what a matrix is, I know some of the math on that, but you don't have to know it. The idea is our whole entire input gets put into a matrix that is the input length, um, the input length wide, and the embedding dimension tall. So 4096 tall and like 7 wide. Maybe. It could be backwards, to be honest. Don't remember off the top of my head. But again, I'm not an expert. This is just concepts. We're going to go with this idea here. We have this matrix, right? Rectangular matrix for this specific sentence. And it's just pointing to these points in 4096 dimensional space and all that. So that is our input matrix. We're going to carry this through. So the next step after this is found, right? There's a big, gigantic matrix that's the whole English language wide and the embedding dimension tall. And then every word, every token just has an ID. And we're like, okay, I know that the is, token 402. So we go to that one and we grab that column and that becomes the, and then cat has one, sat has one, and so on. And then that is updated and trained over time. We'll get to that later. The next thing is position encoding. So it's important for us to encode the position of the words. Sorry, brain is slow today. We want the position of the words to be encoded in this matrix because we can then do it all in parallel, right? So the position you could think is like an additional row that's 0, 1, 2, 3, 4, dot, 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 up to 7. And we kind of add this on somehow. I'm not going to get into the details. It uses sine and cosine on like every other row. And there's some math reason behind it, and I'm not a mathematician, so I'm not sure. But this is the positional encoding. Okay. So by baking that into our input matrix, we then have the ability to go in parallel. We don't have to go one by one. We can do them all at once. And because we know the position, we know like that cat comes before on in the sentence. But we might not process it that way because we're going in parallel. Who knows how long some of these might take? So that is a big thing for just efficiency's sake. You can go in parallel. Okay. So finally, we're going to get into the attention mechanism. Oh, okay. I'm going to briefly go into the attention mechanism. Attention comes from, or the transformer itself is, the big black box. And it comes from a paper that was published in 2017 from Google and a few other places. A bunch of people worked on it. And it was called Attention is All You Need. It's like the paper. I think it's got the most citations of any paper ever in the scientific community across all fields of study. But attention is all you need is where the attention thing comes from. Or with a transformer. Attention comes from a little bit prior, I believe. But again, we're not going to get into the details because attention, in my opinion, is so unintuitive. It does not make sense. But if you study through the history of how it was developed, it's kind of just engineering, like really smart people engineering stuff. Okay, so after the position is encoded, that's our input, and then this goes into attention. So the attention mechanism, make sure we're okay. I could move over here a little bit, but I'll erase as we go. So the attention mechanism is there's three big keys, or three big matrices, I should say, that are involved. There's the Q matrix or the query. And Q is kind of sort of, this might be a bad analogy, but it's kind of just asking the question of what is it? What am I looking for? Also, really, I guess, sidebar, attention corresponds to how words are connected in the sentence. So the cat sat on the mat. Cat probably needs to pay attention to Matt. That's where the cat is at. Um, Poetry. And then sat is also kind of corresponding to cat a little bit. And Matt, right? There's some correlation there. The eh, that's like middle of the road, right? There's two of them anyway. Oh, and this is also important. With the positional encoding, the two thes Sorry, I'm backtracking on myself, but the two thes are now completely different because of the positional encoding. They're at different spots in the sentence. Anyways, the cat sat on the mat. Paying attention to where things are is important. On is your verb. So the cat is doing what? Where? This is where your attention mechanism comes into play. Sorry. The angle is weird, so it might be hard to read. But back to the attention mechanism, the query matrix is we're asking, maybe I'm looking at cat, the cat token. And when I'm asking, what am I looking for? That's what the query is probably going to help us with. But we'll get into it in a second. The next thing is the key matrix. The keys say, what do I have? Or like, what info do I have? So the keys are asking, what information do I have? While the queries, what am I looking for? If you're familiar with computer science, I'll get to that in a second. But the last one is V or values matrix. These are all matrices. That's the thing, it's all matrices. And so it's all just linear algebra, very repeatable processes. And it's why GPUs are very popular for these things because it's just so much tons of matrix operations. GPUs are structured to do that very fast in parallel, a bunch at the same time. But values are kind of asking, don't take this to heart, by the way, but it's kind of asking, what details do I have? Um, Sort of. So kind of like we're looking at cat. We're trying to figure out, okay, this is the subject. Well, what's the verb that goes to cat? We have to pay attention to all of these things. That's why it's called attention. Previous versions of natural language processing used recurrent neural networks, and you'd go one by one, and by the time you get to the end, you start forgetting what was up ahead. So paying attention is necessary for keeping context of what's going on. Um, okay, so QKV. If you're familiar with computer science, this is like queries, keys, and values, very database terminology. It's I don't like the terminology, but I'm not going to I don't like it in the sense of transformers, but regardless, a query is, I'm looking for something, and then if we find a key that exists based on our query, we return and give out the value of that thing. So if I'm looking for, items on shelf B in the inventory software, I'm just making up an example, then the value would be the items that correspond to the key, assuming the key exists. Kind of. I butchered that pretty bad, but um, th that's not this. This is a lot different. So just, if ignore what I said if that doesn't make any sense to you, and if you're like, oh, I've heard of QKV, try to forget the intricacies there. But let's get into the process or the math, I guess. Or okay, not really the math, but just the concept of what's going into the attention process and what comes out. Okay, so there are three-ish stages. The first stage is to get our weights. So there's a weight for the Q matrix, and it's usually equal to your like embedding dimension uh, matrix. So it's a big square matrix, embedding dimension by embedding dimension. So this is, in this case, 4096 by 4096. Huge. Or not too bad, I guess, in computer terms, but it's pretty big for humans. Same thing with the keys, and these are all randomly initialized and they're learned over time, like we've discussed. It's the same for the weight of the keys, and the weight matrix of the values is the same. So once we have these matrices kind of just stored in our model, then we're actually going to set the Q matrix to be our input matrix dot product with the weight Q matrix and some other math. But this basically gives us a matrix that is, sorry, again, my notes. The input length by embedding dimension, the same size as the input up here. So I'll call it input size. Or input dimensions. That might be more clear, I guess, because input size is written somewhere else. Okay, so then same thing with the keys and the values. So just kind of understand that we're just doing a dot product to modify this matrix. Okay, it's just editing these values. And then we have three separate matrices, Q, K, V. Then we compute the attention scores. Okay, so I'll move up here. And again, don't worry too much. I don't know what a dot product is. Just visualize that this matrix is being edited in size. Okay, cool. So your attention scores come from another matrix. Scores, and this is going to be equal to Q times KT, the transpose of what K was. Again, if you're familiar with linear algebra, you're like, oh yeah. But if not, that's fine. This is just concept. So it's just another matrix. And this actually, I think, don't quote me on this, but I think it comes out to a square matrix that's just the input length by the input length. So in our case, this is a 7 by 7 matrix. So it's just 7 across, 7 down, just numbers, right? And 7 by 7, well, then these scores are going to compute what words pay the most attention to what other words. So it tells us all these kind of connections, sort of. It might not necessarily tell us that, hey, the cat is the subject, or I guess I'd say tell the machine that the cat is the subject. It's just knowing cat is very related to Matt in this case. So your scores matrix is some square matrix, supposedly. I might be wrong about the sizes specifically, but we're also going to run it through a softmax. This is just a function or like a mathematical process that converts the numbers. So it's still going to be, it's just 7 by 7 still, and every value or every number inside is between 0 and 1. Because from here, these numbers are just like a bunch of random, I don't know the range of them, but 4, 275, 108, 3, dot, dot, dot. And so these are all just softmax, gets us down to between 0 and 1, so we have percentages to work with. It's a little nicer, a little easier to go. But yeah, look up softmax if you're interested. Finally, we've calculated the attention scores matrix. We need to give an output from the attention block of the machine. And that comes from, so attention output is going to come from your scores dot product with your values, which comes from down here. V is equal to just your input matrix dotted with your value or your WV. And the weights are again learned through training. We'll get to that later. I think that's it. There's more math, a little bit more, kind of helping things out, but this is the concept. And you're going to be left with something that is the exact same size as our original input matrix. It's just, in this case, 7 wide and 4096 tall. Okay, so 7 by 4096 in this example. Okay, so you're probably like, oh, let me tilt that a little bit, but you're probably sitting here thinking, this is really unintuitive. You're correct. I think it's like geniuses figured this out. But the point I want to convey, ignoring any of this, is just it's matrices flowing through a system, just big grids of numbers, or really a list of numbers in a computer. Um, Finally, um, there's one caveat. Some models, it depends on the architecture of the models, but they will use what's called multi-headed attention, or MHA. And it'll take your attention scores matrix, or not scores, I'm sorry. It takes your weights and it splits it and just evenly divides it up. So if you had, this is 4096 by 4096. Divide that by 8, and now you've got smaller matrices with 8 different heads. You can run all of this in parallel with 8 different heads, and then at the end, you concatenate everything to get back to your original matrix. That's the idea of multi-headed attention. But it's just, yeah, it's more parallel processing, which is nice. Let me double check. We're still good. Cool. I have been going on for way longer than I thought. So, but we're almost there, to be honest. But the output, so takeaway, output of the attention scores is the length of your input by your embedding dimension. Finally, not finally, next, sorry, we're going to do the feed-forward network part. So now you're like, oh, that's why we started with a perceptron and a feed-forward network. So, um, So our attention output is the 7 by 4096 matrix, and it's baked with a bunch of info. Info from the Q, the K, and the V. And it's like now we've got these connections just numerically baked into here. Okay. Now, what's next? Feed forward network. This is usually one layer deep. So your input is going to be just your embedding dimension. Okay. And so what we'll do is we're going to do it one token at a time. But actually, it's parallel. So it's a bunch of tokens back to back. They split it and they go down. And that's called mixture of experts. We'll get into that in a second. But the idea is we have, this is our embedding dimension, long. And then this is a token matrix, right? It's one of these. Or it's just a column, a little slice of this one. Okay, and so that goes into this feed-forward neural network. It has one hidden layer, and then it has an output layer that is the same length as the embedding dimension. And so boom, 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 boom. Okay, we have all these connections. This is where the actual learning goes on, and we're learning to produce an output, and the output should make sense. So this is the brain, quote unquote, part that makes a coherent output, and it's using all this attention data to help make this more accurate. That's the idea. So your output of your feed-forward network is an embedding, is, another, something similar to a token. And then you do this a bunch of times across all the tokens. So with all tokens, you end up with, there's 7 tokens here. So we end up with a 7 by 4096 matrix. Pretty familiar at this point. It's just keeping this the same size throughout pretty much all the process. So finally, that is one layer of the transformer. Before I dive into the next layers, mechanisms, I will mention mixture of experts. It's MOE. Mixture of experts is where You basically break your neural network into chunks. And each chunk, right? I've drawn it horizontally, but I drew it vertically here. But each chunk, depending on how many experts you want, they're your experts. Expert two, dot, dot, dot. So you have multiple different experts. And when tokens come into the feed forward stage after the attention phase, where we're breaking this up column by column, they go into literally a router or router, however you say it. So the router, right? So this is your attention uh, matrix columns slash token, right? Basically your token. This comes in and the router is in this middleman. And the router will then tell which expert gets that token. And then it runs a smaller feed forward network. Eventually, maybe expert one gets really good at math, but expert two gets good at translation, and expert three gets good at something else. So the router is also the routing protocol is basically another feed forward network, probably. I don't know the details of that, but the router eventually will decide where to send tokens to which expert. So then if we only need to use expert one, we're saving a lot of computation because we're not doing the full feed forward network. We're just doing one small subsection because the others probably aren't going to give us good outputs, but expert one is really expert at this, right? That routing protocol, kind of like, like an internet router, you got to move data to different computers. This routing protocol, though, is learned in training. A lot of this is learned in training. That's what's also very crazy about all of this. So the feed-forward neural network, at the end of the day, regardless of if it's MOE or not, you're going to end up with the same tokens in a big matrix, same as your input one. Phew. Now, this attention and feed-forward network, that is a layer. So there's two parts of a transformer layer. The attention and the feed-forward neural network. So that's layer one, right? Or if you're computer science, it's layer zero to start. So then the output of this goes to layer two. And layer two is the same thing. Feed forward. This is, layer is equal to, and then output, and then this is layer two. This is layer one, layer two, layer three, same exact process. That's pretty crazy, right? That's just DeepSeek, the Chinese large language model. I think it's by DeepSeek. I guess that's the name of the company or it was, I think, a university that produced it. I forgot. But DeepSeek has 61 layers. ChatGPT, I don't know. You could probably Google it. Or you could, oh man, I'm squatting on the floor. This is crazy. So regardless, there's a lot of layers and they all do the attention and the feed forward neural network. Why a bunch of layers? I didn't talk about convolutional neural networks, but it's similar to a convolutional neural network where layers start picking up on features. Um, so the first layer is kind of dumb. It might only pick up on like the order of the sentence, but then the second layer might find the subject. The third sentence or third layer might find the sentence subject agreement or whatever. The fourth one might pay more attention to the tone. By the time you get to the end of like layer 61, you've got this like more conceptual pattern matching, I guess. Uh, it's a lot of it's a black box because once we start training it, the math just runs over and over until that error is decreased. We don't necessarily know what type of features it is learning. A fun example for neural networks or convolutional neural networks, you can Google it. It's, I think, the husky versus wolves problem in machine learning. They had a bunch of images of huskies and some of wolves, and they had trained it to learn the difference between the two. But then it turns out they photographed wolves in mostly like snowy environments, and then the huskies a more wide variety of environments, I think, or something like that. And it literally ended up learning the snow rather than the actual features of the animal. That was kind of funny. Because then it's like you feed it some other random one and it's going to give you a bad output because there might not be snow in it, but it's still a wolf. Anyways, that's the idea of transformer layers. So I can kind of give a flow chart potentially. Well, I'll give one at the end. The very last step, finally, after we do this rinse and repeat, at the end, so the final layer output is this 7 by 4096 in our example matrix. And this goes into one more neural network, but only the last token. Uh, So it's one more neural network, the embedding dimension, and the very last token, the very last column goes into this neural network with one hidden layer, like the others. And the output of that, and it's softmaxed and all that, but the output of that is every single English word there is. Or actually, they're multilingual, so it's every English word, French, Spanish, German, Chinese, any language that the thing was trained on, the specific model you're using, that is how many of these outputs there are. Similar to how we had 10 outputs for every number, right? 0 through 9 in the very first example. Same thing here. It's giving you a confidence interval, kind of, or not interval, but a confidence rating of the next predicted word. So this gives next token. And that next token is then appended. And then you repeat. Um, so all of that I just spent 25 minutes explaining, or however long, for one word. You can kind of see how people, especially like in terms of energy, this does not use a little bit of energy. This uses crazy amounts of energy. Although matrix math, not much energy, but it's just the repetition and the training is really more thin. So I'll get to the training in a second, but I mean, really, I can just summarize the training in a sentence or two. But the idea of training is you give it a known input, like take half of a Wikipedia article, input it in, and then it's going to predict the next word. Then you check that with the actual article or whatever, you're inputting. And you say, okay, it outputted dog, but the next word should have been cat. So then you back propagate through the whole thing and you train every neural network, you adjust every attention weight matrix or whatever it was. You adjust everything and it takes forever to do that. And then you do that for trillions of examples and it learns the patterns of human speech, or at least human writing. So then you finally get that next word, you add it onto the sentence. I don't know what the next word to this would be because it's a full sentence with a period. You're a helpful AI assistant. Here's the user's prompt, the cat said on the mat. What's the next word? Who knows? Don't, that's a waste. But the point is, we add on the predicted word. And then, for new questions, you're not checking it against an output. You're just hoping that the model is accurate and going to give you a coherent sentence. But you keep going and you keep adding tokens and running again and again until you run out of tokens. Because they're like, okay, we're gonna give free users like 1,000 tokens per prompt, and uh, the whole entire prompt also holds some tokens for previous conversations. Like, oh, the user is someone that likes ABC and they do XYZ based on our past conversations. And so that can also kind of, adjust how it responds. End of the day, it'll run into an end of sentence, and that's usually how it stops. It'll just be like end of sentence, a full thought has been formed. It learned that over trillions of examples, or it learned something like that over trillions of billions of examples. And so yeah, that's it. That's all I've pretty much gotten. So I appreciate anybody that has watched this recording. Um, I hope I was, conceptually correct enough. I'm missing a lot of details, I'm sure, and maybe incorrect about some, but that's the idea. And so when you're working, because I do some work um, regarding this stuff, and it's important to kind of understand what's actually happening, so then you can kind of optimize things. You can try to create custom approaches to certain problems, or you can see bottlenecks, stuff like that. Also for the attention, I forgot to mention that for Q, K, V, K and V are reused throughout the whole prompt, but Q differs per token, so they often will do what's called KV caching, and you store the keys in the values matrix because if you recompute them doing all the weight calculation stuff, it just takes more time. But you can save time by just doing it once and then saving it. But you have to recalculate that every time for the queue for each token. I mentioned KV caching because it's just really popular right now. So is tons of stuff are popular for large language models. Okay, thanks for tuning in. Hope it was all right. And I hope the recording actually converts. So I wanted to append one more recording to say I did have a conversation with ChatGPT right after this, just the cat sat on the mat, period. And it said, got it, thumbs up. It was quite funny, but then I started prompting it of like, what's the history of this? My understanding of the history, and I was actually correct according to this, but the history of Transformers comes from translation because they wanted to translate text. So, for example, that graph I showed, King, Queen, Man, Woman, I stole that from Three Blue, One Brown on YouTube. That's where I first saw it. But the idea of the graph is that it's the vector relation between king and queen, man and woman is about the same type of vibe, I guess. And that's powerful because you can put any language all in the same. ChatGPT said it speaks about 100 languages, but it's most fluent in English, German, a lot of the European languages, Chinese, Korean, Japanese, Hindu, some others. But they put the every language in that huge embedding space. So vectors between man and woman might correspond to like and or femme or whatever, in French. And or whatever it may be in Korean, for example. And so the idea of this representation is that now you can translate, but not just dictionary by dictionary definition, but you can translate by tone and intent and context, which is more powerful than just looking up a dictionary word for word, especially with formalities. So then I put it, okay, translate this into Korean or Chinese, or I did a completely different language to English, so it uses different symbols as well because it has that power. But then I was like, bro, hop on VC, right? Like voice chat. I tried to think of maybe that's not what people say, but I tried to think of a dumb sentence like hop on VC, let's run some fort, you know? Like which, in English that means, let's hop on and play Fortnite. And so there's obviously got to be some like slang in other languages. Like imagine a Japanese kid being like, yeah, let's play some Fortnite. But like What does that sound like? Google Translate, well, it might not be able to tell you that, although Google Translate probably uses transformers anyway. So anyway, I just wanted to add that on. It was kind of a fun little like addition. But anyway, that's it.